We want to develop strategies for how to go from one type of information in a problem to another type of information. And already, what we have on the board is one type of problem that we could answer. Let's suppose that I give you an equation for a line. How can you determine from that equation what the slope of that line is? What role is the slope playing in the line, in the equation y equals mx plus b? For example, if I were to give you the equation y equals negative 4x plus 1, what would you say is the slope of that line? 4x? Negative, okay, so we got a couple disagreements. Is it negative 4x? Is it negative 4? Is it 4x? Mike, explain your reasoning here.
I think it's negative 4 because whatever you plug in as x, that'd be the slope.
Right, so the role that the slope plays in the line equation y equals mx plus b is the slope is this coefficient of x. This is m right here. It's that number which is multiplied by the x term in the equation. So the first thing to notice about a slope is that it's always a number, at least in our class. In calculus we play around with that, but in algebra and in pre-calculus, slope is always just a number. It doesn't have a variable as part of it, even though in the equation y equals mx plus b, the slope gets attached to that variable x as a coefficient. But if I have an equation and I want to just read the slope off of it, then all I'm going to do is just select the coefficient of x. Coefficient of the x is how we read the slope off of an equation, y equals mx plus b. So that's how we can go from an equation to a slope. Very often, though, the world does not hand us an equation on a silver platter. In fact, most of the time that's not what happens. This is, I think, one of the topics in our course that is the most closely connected with the kinds of ways that you can use data and information from the real world to do some process of what we call algebraic modeling, to discover an equation which fits a set of data that you've measured out there in the real world. Maybe it's market research data. Maybe it's discrimination diagram data for a mineral combination. Maybe it's velocity time data on a driving car, something like that. Data that we've collected from out there. We can use what we're learning in this module to model that data using one of these kinds of equations. So one of the other sources of information in our module is going to be points. How many points do I need to choose before I have determined a line? Let's start with that. How many points do I need in order to determine a line? 2. So if I start with 2 points, we should be able to use those 2 points to determine an equation in the form y equals mx plus b. Typically, though, so I'm going to call those 2 points something. I'm going to call them, so every point we can represent as an ordered pair, an x coordinate and a y coordinate with a comma. But if I have 2 different points, then I have to give those points 2 different names. And so typically the way that we'll denote them just using variables is we'll use subscripts. So the first x and the first y, and then the second x and the second y. And if I have that information, if I have 2 points that I've collected in data somewhere in the world, I can use those 2 points to determine a slope. How do I do that? Let's do this with an example for starters. Let's suppose that I give you this table of data. And I'm not going to put any context onto these variables for now. We're just going to call them x and y. And maybe I give you, as data points, 1, 5. And for my second data point, let's make it 4, negative 4, or something. So in other words, I'm giving you 1 point that has the coordinates 1, 5. So to find that point, I would start at the origin here in my coordinate system. I'd go 1 step to the right in the x direction, and then I'd go 5 steps up, 1, 2, 3, 4, 5, and locate my first point, 1, 5, right there. So I'm kind of using the graph grid on this diagram here, 1, 5. And before I go any further, I should make sure to label that my vertical axis has my y values and my horizontal axis has my x values, as is conventional That's just typically the way that mathematicians use the letters x and y in this context. But when these variables have meaning outside of abstract mathematics, we might do that differently. But for us, as long as we don't have any specific meaning attached to these, or any sort of input-output or dependency relation, we're just going to use x on the horizontal and y on the vertical. So 1, 5 is that point, which I've marked, which is 1 unit to the right of the y-axis and 5 units up from the x-axis. So then 4 comma negative 4 I'll locate the same way, by starting at the origin, and then from the origin moving over 4 steps to the right, so 4 steps in the x direction, 1, 2, 3, 4, which puts me there. And then from there, 4 steps down, because my y-coordinate's negative. That places 4, negative 4 right there in my coordinate system. 4 comma negative 4. So, Effendi told us that once we have 2 points, as long as they're not right on top of one another, those 2 points are going to determine a line for us. I'm going to sketch that line in here in red, so you can kind of see what it looks like. Nudge this over a little bit, make sure it actually goes through my points. There we go. So there's my line. And so the question that I have now, and this is where we get to grapple with what slope is, what it means. What are we to understand the slope of this red line to be? What's it supposed to measure? When you think of the word slope, what does it make you think of? Or where else do you hear this word in everyday conversation that might give us a clue? The first thing that slope might make us think about is distance, is some way of measuring along this line. One notion of distance that we could get off of this graph is literally just the distance from one of these 2 points to the other. Right? If I just joined 1, 5 to 4, negative 4 and asked how long is that line segment that I just drew, I would get some number. What would I get in this example? 3, 9 plus 8 is the square root of 90. So 3 times the square root of 10. I would get about 6.6 or so. Back of the envelope, 6, maybe 7. I don't know, somewhere in there. Some number between 6 and 7. So that's going to give me some number, the distance between these 2 points. The problem with distance is this. The number that I get for the slope of a line should not depend on which points on that line I choose. This is the challenge. I want to find a way of computing a slope that doesn't relate to individual points on that line, but which is a characteristic of the entire line, regardless of which points I chose. So if I chose these 2 points on this red line and I measured the distance between them, I would get some number between 6 and 7. But if I chose a different pair of points that were maybe closer together, I would get a different number for distance. If I chose different points that were further apart, I would again get different numbers. So I want whatever the slope of a line means, it needs to mean something that doesn't depend on which points I've chosen, but which only depends on which line I drew. So if it is to be a distance, it can't just be a single distance, a single measurement. It has to be something which, as we go to different points along this line, will remain the same nevertheless. So how do we get there? How do we get to a way of measuring something about this line that only depends on the line and not on the points that we choose along that line? So rather than thinking of slope as a single distance, what I'd rather think of it as is a comparison between distances. In particular, as we go from one point along this line to another, the x-coordinates of our points are changing, and the y-coordinates of our points are changing. If we only focus on one of those 2 measurements, we're going to miss what's happening with the other one. So in order to be a measurement of something that only depends upon the line and not on the points that we choose, we need to set up a quantity which is a comparison between x distances and y distances. In other words, we need a number which can compare for us the amount that we move left to right along this graph versus the amount which we move up and down along this graph. More to the point, if we think about the distance between these 2 points that we sketched, we're thinking about this black segment that I just drew on here, but that's going to be different from one point to the next. Instead, here's what I want to think about. I want to think about the vertical and the horizontal components of that distance separately and make some kind of comparison between the 2 of them. So what I just did was I just sketched in this little right triangle. We're going to do a little bit of geometry, not a lot. just a little bit of geometry on this diagram. So in this right triangle, the hypotenuse, this segment right here, which is opposite to the right angle, that measures the distance between these 2 points. It's only a single distance. We didn't want that. Instead, what we want to do is compare the width of the segment up here and the length of that segment over there. So first, let's set about that task by actually measuring. How long is this horizontal segment that connects my blue point at 1,5 to this point right here? In other words, how much horizontal distance separates these 2 points? Say that again? Is it four points away? So starting from here, go 1, 2, 3. So it's 3 points away. And where could we have gotten 3 from the information that we knew about this line? Yeah. So we can measure the distance, this horizontal distance here, by subtracting my 2 x coordinates. So by subtracting 4 minus 1, 4 minus 1 gives me positive 3. And that positive 3 is this distance right here. And I'm going to think of it as a directed distance. I'm going to think of that plus 3 as meaning in order to go from the first point to the second point, I need to take 3 steps to the right on my coordinate system. And I can measure that again just by subtracting the 4 minus the 1. So that's the horizontal separation. How about the vertical separation? In order to get from my blue point to my orange point, how much vertical distance do I need to cover? Okay, and how'd you get that number? Yeah. So we could count grid squares on the graph if we were doing it graphically. To go from here down to here, we have to go down 1, 2, 3, 4, 5, 6, 7, 8, 9 units. But to do it with arithmetic, we would do the same thing that we did with the x's and just subtract. Negative 4 minus 5. That would give me negative 9. So subtraction here in algebra is our tool for measuring distances, or measuring differences, if you like, on this graph. So now we have 2 distances. We have a 3, which tells us we're going to the right 3 steps. We have a negative 9, which tells us we're going down 9 steps. We need to compare those 2 things together in a way which is not going to change if I pick these 2 points that I picked, or if I instead pick any other 2 points along this line. For example, if I were to choose, I don't know, this point and this point, so these 2 points that are a lot closer together, I would measure their horizontal distance, their vertical distance, and I should still get the same slope out of that calculation. How do we make that happen? What should I do with this negative 9 and this 3? Simplify what? So before I can simplify, I have to do something in arithmetic. We've done the subtraction to measure the distances. What operation are we going to do to make a comparison between these 2 numbers? Let me give you a bit of a hint that might ring some algebra bells. What we really did with our x values is we subtracted the second x coordinate minus the first x coordinate. So that's what we really did there, if you use our notation from before, is we did x2 and x1, and we subtracted them. So that's where we got our positive 3. Ditto with our y coordinates. We took the second y coordinate, y2, and we subtracted the first y coordinate, y1. And so where this positive 3 and this negative 9 came from is they came from, respectively, x2 minus x1 and y2 minus y1. There is a formula that you probably remember or have used, probably pretty recently, that puts the difference in the y's and the difference in the x's together to get a slope. What operation does it use? y2 minus y1 and x2 minus x1 get operation which is going to remain the same regardless of which 2 points we choose along this line, takes the horizontal and the vertical differences and it divides them. y2 minus y1 divided by x2 minus x1. That is a definition of the slope that joins the point x1, y1 to the point x2, y2. So this formula is what we can use to make that translation. If I start with 2 points and want to determine a slope, that's where I can plug in that formula. And often, especially in calculus, this will get called, it goes by another name, it'll get called the rise divided by the run. Rise here meaning the vertical difference between 2 points on the graph, and the run meaning the horizontal difference between those 2 points on the graph. So every slope is a comparison between rise and run. So if we do that in our example, we'll take the rise, and remember the rise is the y's. And so the y's end up on the numerator of this fraction. They end up upstairs. The x's are the run. The difference in the x's is the run, so they're the denominator. And so by dividing the former by the latter, I get a single number, -3, which we can call the slope of this line. That right there is a core skill in this module, to be able to take 2 points and to determine the slope of the line that joins those 2 points. That's a skill you're going to use a lot, over and over and over again in Module 4.